Today we start the chapter that is scalars and vectors. Uh, we learn this chapter within the subject of engineering mechanics. Therefore, first you have to understand what is engineering mechanics. Engineering mechanics is basically a branch of science that deals with the effects of forces on a body which may be at rest or in motion. Therefore, actually, we are studying the effects of forces on a body. To understand these effects of forces, you have to understand the quantity, that is scalars and vectors. And for this engineering mechanics, sometimes for the higher order term, you have to understand the tensor. First, we discussed about the scalar and vectors. Why these scalars and vectors are actually required in engineering mechanics. It is actually required to describe the quantities. Suppose if you want to describe about the force which is act on a body, then only the magnitude of this force is not sufficient to describe the phenomena. You have to give the direction also. Okay. Similarly, to describe the velocity, acceleration, we need the scalars and vectors. Uh, Now you see that the scalar is actually used to describe the quantity which have only the magnitude, like time, volume, density, speed, energy, mass, etc. Whereas the vector is used to describe the quantity where the direction and magnitude both are required. Now I give an example that if I ask you how many mobiles you have, then you can say uh, one or two or maybe three, like that. Now your answer perfectly satisfactory. This bare number 1, 2 or 3 is a magnitude which is sufficient to provide the information. Similarly, if I again ask you how far is your house from your college, then if you say suppose 3, then it is not sufficient to answer my question. Means more information is required. Now if you say 3 kilometer, now the number 3 is named as representing a certain number of kilometer. Then your answer becomes satisfactory. Such numbers are sometimes called scalars. temperature, the total energy of a thermodynamic systems are also represented by a scalar. Now, if I again ask you, how can I go to your house from your college location? And then, if you say just walk 3 kilometers, then this information is not sufficient to answer my question. Some more information is required about the direction. Then, if you say just walk 3 kilometers due north, then your information is okay. The number 3 kilometers now has the required additional directional information attached to it. Such numbers are called vectors. Suppose velocity or force all all are vector, since it has a magnitude and as well as a direction. Physically, vectors are used to represent locations, velocities, accelerations, flux densities, field quantities, and etc. The defining equations of the gravitational field in classical dynamics, that is Newton's law of universal gravitation, and of the electromagnetic field in classical electrodynamics, that is Maxwell's four equations, are all given in vector form. Since vectors are higher order quantities than, the scalars, the physical realities they correspond to are typically more complex than those represented by scalars. Therefore, basically, this scalar, vector, or tensor is actually used to describe the measurable quantities. When in case of measurable quantities only magnitude is sufficient to describe the quantity, then we use scalar, or that quantity is scalar. And when the quantity requires to describe that quantity, if it is the magnitude and the direction both are required, then it is vector. And for here it is written, that is displacement, velocity, acceleration, etc. And for the higher order term, that is for stress in case of classical dynamics, or permeability in case of classical electrodynamics, tensors are used. These tensors are used for the higher order term. I discuss this topic, this tensor, later. Now we concentrate only on this scalar and vector. Here, this parallelogram law, that is used for the addition of the vector. This parallelogram law is required, and we can sometimes use the triangle law also for this addition in vector, because in vector algebra we cannot add two vectors directly. We have to use this parallelogram law or this triangle law for the addition purpose. We discuss this vector algebra later. Now this thing is already discussed, that in case of scalar, only magnitude is associated, and in case of vector, the direction as well as magnitude both are associated. Now, in case of addition of two vectors, we can use this parallelogram law or this triangle law. If this v1 is a vector and v2 is another vector, to add these two vectors, we can use this parallelogram law or this triangle law. In this parallelogram law, suppose this one is your v1, v1 is the one vector, that is this one, and v2 is another vector. If we represent a parallelogram where the two adjoining corners are representing two vectors, that is v1 and v2, then this vector, this resultant vector, this one is the resultant vector. If we join the two corners, then we get the resultant vectors of these two vectors v1 and v2. The length of this vector gives the magnitude, and this arrowhead describes the direction. Similarly, this length is the magnitude of this v2 vector, and this arrowhead describes its direction. Then the length of this resultant vector define the magnitude of the resultant vector, and this arrowhead describes the direction of the resultant vector. Similarly, in case of triangle law, if we place these two vectors in this way, where the arrowhead of one vector is attached to the tail of the another vector, that is v2 here, then if we join from this point to this point, here this length of the vector actually defines the magnitude of the vectors. And if we join in this way from this point to this point, then this vector is the resultant vector of this v1 and v2. It is actually the these resultant vectors we get after the addition of this v1 and v2 vectors, and this arrowhead is describe the direction of this resultant vector. In this way, either by this parallelogram law or by this triangle law, we can add two vectors. Here, vector v can be written as this v. Here this v is the magnitude, it is not the vector, it is the scalar quantity, it is only magnitude. V, and it is the unit vector which defines the direction. Actually, we are representing this v vector by this magnitude of the vector v and the unit vector which is defines the direction of the vector. Okay. Here it is written that it is the unit vector whose magnitude is 1 and whose direction that of vector v. Unit vector, how we can get this unit vector? Unit vector can be formed by dividing any vector such as the geometric position vector by its length or magnitude. If we divide this vector by the magnitude of this vector, then we get the unit vector. And in case of Cartesian coordinate, we describe this vector with the help of ijk, where this ijk is the unit vector along x direction, along y direction, and along z direction respectively. Now we discuss about the types of vectors. First, we discuss about the fixed vector. Fixed vector is a vector which have constant magnitude, that is the fixed magnitude is there, and also the direction is fixed. And in case of fixed vector, that is why the there has unique point of application, like that. Here these force vectors are fixed vector because it has constant magnitude and also direction, and it has the unique point of application. The example of fixed vector is the force on a deformable body, because in case of deformable body, the point of application of the force is very important, and if the point of application of the force is fixed and the vector has a constant magnitude and direction, then it is a fixed vector. Now the second type of vector is sliding vector. In case of sliding vector, it has also the constant magnitude and direction, but it has no unique point of application. In place of that, it has unique line of action. Okay. Means the force can act anywhere within the line of action. That is why no unique point of application. The line of action is unique, but there is no unique point of application. And the vector can slide along the line of action. It is the example of sliding vector. In case of this rail, force may be applied here or force may be applied here. The effect on this rail is same. Means if we draw a straight line from this point to this point, then we can apply force anywhere within this line of action. Okay, but here the point of application is not perfectly defined. That is why it is sliding vector. In case of sliding vector, we use the principle of transmissibility, which actually defines the application of force at any point along a particular line of action. And there is no change in resultant external effects of the force. This type of sliding vector or force, this kind of force is actually applicable for the rigid body. We can use this type of force in rigid body only. If this one is the object and if we apply a force here, that is P, and if we draw the line of action here in this way, then we can place this force P anywhere within this line of action, and there is no change in their results within on this body by applying the force. That is why it is sliding vector, and we use here the principle of transmissibility. Therefore, we can, here you see, if this one is the object and if we apply a force here and if we draw the line of action by this dotted line, then we can place this force anywhere within this line of action, and the result we get for both the cases are same. It is applicable for the rigid body. Now here the principle of transmissibility is written that the external effect of a force on a rigid body will remain unchanged if the force is moved to act on its line of action. In other words, a force may be applied at any point on its given line of action without altering the resultant external effects on the rigid body on which it acts. Means, suppose for this car, if we applying push here and if we draw the line of action, push is actually the force, and if we draw the line of action of this push by a dotted line, then we can replace this push by this pull. If this pull force acts on the same line of action, then we get the similar result if the direction and the magnitude of the force is same. Then whether it is push or pull, the net effect on this object is remain unchanged. Now the third type of vector, that is free vector. In case of free vector, it can freely move within the space. There is no unique line of action or no unique point of application. That is your free vector. The example is moment of a couple. Okay. For this purpose, the vector, that is the moment of couple, where the line of action and the point of application is not defined. That is why it is free vector. Now we already discussed about the parallelogram law for the addition, vector addition. Suppose this one is the one force, that is F1, that is the vector obviously, and this one is the F2, another vector, which actually represents the two adjoining corners of a parallelogram. Then if we join the corners of this parallelogram, actually represents the resultant vector or the of these two vector. and we can add two vectors by algebraic solution. We discuss it later using the coordinate system and also by the geometry, that is from the law of cosines and law of sines. Okay, we discuss it later, but uh, main two types of addition is required, that is for our case, that is for parallelogram law and the algebraic solution. Now we can use this parallelogram law or the triangle law when the forces are concurrent. Now what is concurrent? The forces are said to be concurrent at a point if their line of action intersect at that point. We can apply this parallelogram law or triangle law when the forces are concurrent. Okay. Now how we can represent a vector? Suppose this one is a vector v which makes the angle theta with the horizontal line. Then this vector v is represented by this v, that is only the magnitude, and this one, this cos theta I plus sin theta j, is actually the unit vector. This I and j is the unit vector and it describes the direction. Okay. These two are the unit vectors. We can represent any vector in this way, that is vector v is equal to the magnitude of vector, and this term defines the direction of the vector. And we can also represent any vector if the coordinate is known to us or we know the slope. Here we can represent it this way, any vector. And if we know the coordinate of any 2 point within the line of action of this vector, then we can calculate the unit vector in this way. Suppose this one is x1 y1 and this one is x2 y2, then the unit vector is, suppose this one, suppose this one, it is x2 comma y2 and this one is x1 y1, then the unit vector becomes x2 minus x1 I plus y2 minus y1 j divided by, it is the position vector, x2 minus x1 I plus y2 minus y1 j, it is the position vector, divided by the magnitude of this position vector, that is root over x2 minus x1 whole square plus y2 minus y1 whole square. Then this total thing represents the unit vector along this direction. Then we can represent this vector v by the magnitude of the vector into the unit vector that defines the direction. Now we solve a problem. Here you have to determine the x and y scalar components of F1, F2 and F3. There are three forces acting at a point A on the bracket. Okay. Here the slope is given. Here the angle is given. And for this case, we can easily find out the coordinate of B point and this A point, because here the dimensions is given. Along the x direction it is 0.2 meter for A, and along y direction it is 0.1 meter for A. And for B, if we take this point as the origin, then for B, along the x direction the displacement is 0.4 m, and along y direction it is minus 0.3 m. Okay. Now for the first case, for F1, we can write the vector F1 is equal to F1, that is the magnitude, into the unit vector. And we can write the unit vector in this way, that is F1 into cos 35 cos theta I plus sin theta j, that is the position vector, divided with the magnitude that gives you the unit vector along this direction. That is why to define the unit vector we actually divide the position vector by the magnitude. It is already discussed. From that principle we get this unit vector along this direction. Okay. Then this becomes this one, and here the magnitude of the force is given, that is 600. Then automatically from this we can find what is F1 vector. F1 vector here it is 491I plus 344J. Now the magnitude of this F1 force along the x direction is 491 Newton, because this I is the unit vector along x direction and J is the unit vector along y direction. Then automatically the force component along the y direction for F1, it is 344 Newton. Now for second case, where the slope is given, we can easily find out what is the value of this unit vector N2, which acts in this direction, because the magnitude of the force is given here. Then it is, we can apply this force magnitude is 500 Newton, and we can find out easily what is the unit vector, because this minus 4i plus 3j is the position vector along this with respect to this slope, and divided by the magnitude we get the unit vector. And if we multiply this magnitude of the force with this unit vector, then we get the vector form of this F2 force. Now we can easily say that this 400 Newton is the x component of this force and 300 Newton is the y component of this force, because this I and j is actually representing the unit vector along x and y direction respectively. Now we have to find out for this F3. Now for this F3 we can write the position vector in this way, that is, we know to find out the position vector if we know the coordinate. Here we write the coordinate. For this case the coordinate is, for x it is 0.2 and for y it is 0.1, and here for b it is 0.4 comma minus 0.3. Now if you recall the how we can write the position vector, if this one is x1 y1 and this one is x2 y2, then we write the position vector in this way, that is x2 minus x1 I plus y2 minus y1 j. Actually we write this thing here, that is x2, that is 0.4 minus 0.2, that is why it is 0.2 I, plus here y2 is minus 0.3 and y1 is 0.1, that is why minus 0.3 minus 0.1 becomes minus 0.4 j. Then we can automatically get the magnitude in this way. Okay, this is mod of this position vector, just root over of 0.2 square plus minus 0.4 whole square, and we can represent this force F3 in this way, that is F3 for magnitude, that is 800 Newton, and N3 is the unit vector along this AB. That is why we did in this form, and we get the vector form of this force, that is for 800 Newton is this one, and automatically we can say the x component of this force is 358 Newton and y component of this force is 716 Newton. Now if we want to determine the resultant of these two forces which acts on a bolt A, here the forces are given, the magnitude of the forces are given, and what is the angle made with the horizontal axis for this force is given, that is 20, and what is the angle made by this force with this P force is given, that is 25, and we have to determine the resultant. Here we can write that it is the algebraic solution of this vector sum. We actually want to find the resultant force of these two forces. That is why we written here that R vector is equal to P vector plus Q vector. Now we can write the vector form of this P vector because the resultant vector is known to us, and we can easily write the P vector. It is the 40, this is the magnitude, and it is the vector, it is the direction vector, that is cos 20i plus sin 20j. We can easily find out what is the value of this P vector. Similarly, for Q vector, we can write it is the magnitude of the force, that is 60, and the total angle made with the horizontal axis is 20 plus 25, that is 45. That is why it is written cos 45i plus sin 45j. And we can easily find out what is the P vector and what is the Q vector. Once you get this P vector and Q vector, you can easily add this two vector to get the resultant vector in this way, that R vector, the resultant vector is equal to this 37.58i plus this 42.43i, that becomes 80.01i, and this 13.68j plus this 42.43j, that is 56.10j, and the magnitude of this resultant vector becomes 97.72. We get this thing from this way. How we can get this thing? If we want to find the mod of R, the magnitude, then we have to write this root over 80.01 square plus 56.1. We get this resultant vector. And how we can get this alpha? We actually get this alpha if we just, alpha is the angle made with the resultant vector. Alpha is the angle made by the resultant vector with the horizontal direction. We actually get this thing by alpha is equal to, for this two-dimensional case, we can write this tan inverse the coefficient of y direction, that is 56.1 divided by 80.01. Okay, you can calculate this thing, that is tan inverse of 56.1 divided by 80.01 Okay, now it is sufficient for first lecture. We discuss the later portion in our next lecture video. Okay, thank you.